Hello and welcome to Cloud Security Masterclass. Today we are diving into another GenAI demo. If you saw my previous video, I showed you how GenAI could be used to do natural language analysis of AWS IAM permissions. This time around, we'll be using GenAI for another very interesting use case, creating custom cloud security requirements for an organization. We'll be coupling our AI model with another very prominent technology called RAG, or Retrieval-Augmented Generation, and we'll be using Google's Gemini LLM model and Vertex RAG Engine for this demo. So, ready to see how AI can transform cloud security? Let's get started. Alright, first off, let me share some thoughts on why generating cloud security requirements manually can be a big challenge. So you can really appreciate the solution that we are about to explore. From the very start, as companies migrate to public cloud, they need to define these set of requirements for the multitude of services that the cloud provider offers. This is to help their engineers to be able to securely deploy services into production. But how do they do that? First off, every company has corporate security policies, which are a set of high-level rules or requirements for any IT services in their organization to follow. Secondly, cloud providers like AWS, GCP, and Azure, they all publish tons of documentation around how to configure their cloud services. So now the task of creating custom cloud security requirements involves merging these two sources, the company's internal security policies and the cloud provider's documentation, to come up with these custom set of cloud security requirements that are actually relevant and specific to the organization. Now, here's where things get really tricky. First, the sheer number of services that these cloud providers provide is huge. In GCP alone, there are more than 200 services, and companies today are using more than just one cloud provider. So you might be using AWS, Azure, and GCP, and the services that you might be using from the cloud is huge. Second, the depth of knowledge need to configure these services properly. Let's take a simple example. For configuring GCS buckets, Google Cloud offers more than 300 documents. Yes, 300. And that's just one service, right? So imagine this. A human needs to go through all of this documentation, then decide which of these configurations matter, and then map it to the corporate security policies. It's tedious and manual job, and honestly, it's very painstakingly slow. And this is exactly where AI comes in. What if AI can make this easier, even more effective than doing manually, right? This is what we're going to see in the demo. We'll use GCP Gemini AI model and Vertex RAG Engine to generate custom security requirements for cloud storage buckets. We'll imagine a fake company with a fake corporate security policy, and that is what the demo is going to be. So let's start the demo. So in order for us to create cloud security requirements for cloud storage bucket, we have two sources. One is the company policy with the company standards, and the second is the cloud provider documentation around configuring cloud storage. So let's take a look at the latter. This is the documentation that GCP provides and how to configure the GCS buckets. And as you can see, this is cloud.google.com/storage/docs. Now, in this folder, we have all the documentation. So if I go and click on the read product overview, I'll be going to the introduction page, and all the other pages like creating buckets are a subfolder within this docs folder, right? And you can see the huge amount of documentation around creating buckets, managing buckets, uploading buckets, and updating buckets, managing buckets. And there's a ton of security information here around access control. For example, how to make your data public within and GCS bucket. So what we want to do from an LLM standpoint is we want to feed this information to the LLM for it to understand the security configurations that could be done for this bucket, right? And imagine if you're a security engineer trying to do this manually, you would have to understand how this product functions, which is understand how these buckets are created, what can you do from a developer standpoint, and you would also then need to go from there to figure out what security configurations can be enabled on this by default so that the deployments are secure. So it's a very tedious task. As you can see, there's lots of documentation around this. So what I'm going to do now is I'm going to download all of this information locally and then store it in a GCS bucket. So I have a small like a wget command to download this all of those HTML files locally, right? And this is the command that I'm using, and it's basically downloading all the HTML pages within this directory. But there are many pages which are like specifications for the JSON API, or some references or some release notes. All of this is something that I don't want, so that's why I'm excluding these directories. And also there are some pages which are in different uh, languages, right? So example, some which is in Italian and some in Spanish, and obviously I don't want those pages, I just want English. So I'm explicitly excluding those pages here as well, right? So this is the wait command that I'm using to download those pages, and I've already run this. And this might take, some maybe 5 minutes to document to download all those pages, and I'll pause the video and come back to it once this download has been done. Okay, so the script completed successfully, and as you can see that it converted links in 301 files. So there was a like ton of documentation around GCS from GCP. And let me show you in VS Code how this data looks like. So we had a folder created here called cloud.google.com, and within this folder we have different documentation. Um, Pretty much the important thing here is the documentation within storage, and within storage within docs, and you can see all the important GCS related configuration, these HTML files, best practices, um, collaboration.html, and the important ones from a security standpoint like access control, authentication, they're also here, right? So now what we're going to do is we are going to copy this information to a GCS bucket so that we can feed this into our RAG database. So I've already logged in to this command line to my GCP account, and I'm going to be using the gcloud storage buckets create command to create this bucket, which will store all of this GCP documentation. The bucket is created now. And then I'm just going to do the gcloud storage command to copy all of my data from this location to my GCP bucket. And again, this will take some time to go through since it's a lot of files, but I'll pause this video and come back when this is done processing. All right, so the upload of objects to my GCS bucket is now complete. As you can see, there is a total of 287 files that are copied over to the GCS bucket. Let me switch over to the console and show you how the GCS bucket looks like now. So here's I'm in the GCP console, and if I click on my bucket, I can see there's a folder docs here, and within docs I have all these different folders for different types of configurations. Within access control I have all these files. Within authentication I have all these files. So my data is in the GCS bucket now. After my data has been uploaded to the GCP bucket, what I need to do is now create a RAG corpus, which is a retrieval augmented generation system in GCP using the Vertex AI RAG Engine. These are the input parameters that are going into the script: the project ID, the display name, which is a identifier for the RAG corpus, the location, the region where the script is running, and the paths. This is the location for all the documents, the GCP bucket that we just created. First step is initializing the Vertex AI API. Um, and the first configuration that is very important from a RAG standpoint is configuring the embedding model, the model that will be used to convert all the textual data into the numerical representation of that data so that it's machine understandable and machine readable, right? So we're using a pre-trained Google model called Text Embedding 005 for this purposes. And this model, as I said, would convert our text into vectors. And that vector pretty much means the numerical representation of that data for it to be understood by the LLM. This next config would be creating the backend database, which is the vector database, using this embedding model configuration. Then we'll create a RAG corpus. Corpus here basically means a group of documentation that goes into the RAG. And we'll create this corpus using the backend configuration that we just created above, and we'll print out the name for this RAG corpus. Configuration here is the transformation config, and this is a very important configuration because this is will help to break down your documents into small pieces called chunks, and before they're stored in the RAG system, right? And this is done by this transformation config, within which we have the chunking config, and the two important configurations here are the chunk size and overlap. Chunk size of 500 means that each document will be split into chunks of 500 tokens. And think of this as dividing a very large document into small paragraphs, which are more manageable and smaller. Um, and then the overlap means that each chunk will overlap with the previous one by 100 tokens. And this ensures that the context between those chunks is not lost, and therefore it's very useful for maintaining the accuracy of the retrieval. So in summary, these two are a very important configuration for RAG for it to be able to retrieve the data and to be able to reason on that data accurately. So your chunk size has to be just right, not too big so as to not overwhelm the model, but it shouldn't be too small so the important context is lost. So it has to be just the right size. So play along with these two numbers depending on what kind of data you're bringing into the RAG. Another important thing that we have to do here is we have to import our files from the GCP bucket, which are mentioned in the path, in using the transformation config that we just defined above. And that's it. That's the steps that we are doing in the RAG, not create RAG-create py. Next, I'm going to go to the command line and run this Python script. Now, this would take some time. Obviously, it depends on the number of documents that are being uploaded into the GCP bucket, and also it depends on the chunking configuration, the size of the chunking and the size of the overlap. So it depends on those factors, but it should take around 5 to 10 minutes to go ahead and create that RAG with all the documents. So as you can see, it has already created the corpus here. And the next step would be for it to upload all those documents into this corpus using the embedding model that we have provided and the chunking and the transformation configuration. So I'll pause this video and come back when the RAG corpus is created and ready for us to go forward. All right, so this was surprisingly fast. It just took about like a couple of minutes to go through. And as you did already see that the corpus was created, but we also see that the 287 files that were there in the GCP bucket have now been copied over in the vector DB in the embedding format. So, and this is a quick check as well that we have 287 files in RAG, and we also had 287 documents in the GCP bucket. So all of those have been copied over to the RAG corpus now. Now let's do a quick summary of what we have done so far. So we started off with 287 web documents around how to configure cloud storage buckets provided by Google Cloud. We copied those 287 documents into the cloud storage bucket, right? From there, we use the pre-trained GCP provided model for embeddings, and we converted those documents into our embeddings or vectors and stored them into a RAG vector DB. And as a quick check, we started with 287 web documents. Those are now converted into 287 files in RAG. So let's go forward to our next step and see how we can retrieve this data from the RAG now. Right, so now let's take a look at how we can retrieve the information from the RAG. And there are two basically different mechanisms on how we can do that using the Vertex AI engine. So I'm going to show you both of those in a bit. The input parameters to this script is going to be the project ID or of the GCP project, the location or the region where this project is running, and the corpus name. Now this is the same corpus name or the RAG corpus that we created as part of our RAG create script. So the two methods, let's go through both of them. The first one is direct context retrieval, right? And here in this direct context retrieval, we're running a retrieval query, and we are passing first of all the corpus for which we want to get the data from, right? And here we have option of actually specifying individual files within the corpus as well. But since we are trying to retrieve data on all the configurations for Google Cloud Storage Bucket, we are going to do this on the entire corpus here. The second is the question or the text that we want to search in this corpus, right? So in our case, we are searching for all the security requirements for Google Cloud Storage Bucket. So that's our text. And the third piece of information is the retrieval config. And the retrieval config has two parameters. One is top K, and top K is basically asking the model to retrieve the top 10 most relevant chunks of information. And then we also have a filter parameter, which helps to narrow down the results based on similarity. So here we are only keeping items where the vector distance is less than 0.5. So only closely related content will be returned. So this is the direct context retrieval method, and we will in the script we'll be printing the response with it, so you can see what is the output of this retrieval. All right, so the next method that we'll be using for retrieving information from the RAG is using a RAG retrieval tool. And this is really where things go to the next level because we are not just retrieving information from the RAG, we're actually clubbing this information in a tool. That tool would be embedded into a GenAI model for the GenAI model to have additional context in answering questions. So instead of creating a query, we are now creating a RAG retrieval tool, and we're still passing the same parameters as before. So we are passing the corpus name and the RAG retrieval config, which includes the top K and the filter, just exactly as before. So the parameters are not changing. But instead of directly retrieving the output from the RAG, we are creating a tool, and we are passing this tool to the GenAI model. The GenAI model that we have here is Gemini 2.0 Flash from Google. And then we are asking the same question as we were asking before, generate security requirements for Google Cloud Storage Bucket. But this time it's being answered by the AI model using the information that it gets from the RAG to supply additional information and context to be able to better answer this question. And also I'm finally generating the response. So I will run the script now and show you the two different outputs that we get from the script for you to better understand how these two retrieval mechanisms from RAG works. I ran the RAG retrieve Python script, and this is the output that I got from the direct retrieval query. And as you can see, it has multiple context within it, and this is just one chunk of information that it could find that's similar to my query, and my query was cloud security requirements for Google Cloud Storage Bucket. And as you can see, this text is the information that's coming directly from the RAG, and you see the length of this is less than 500 tokens because that's what we set as part of a chunking rules in the RAG. And we also have some similarity score here. This suggests that how similar this particular text is to the query that we provided as part of input in the retrieval. And so this should not be more than zero point 0.5 because we set that filter as zero point 0.5. The smaller values are more closer to the initial search query. Um, so yeah, this is the output from the direct retrieval. It doesn't look very pretty, but again, this is just finding similarities um, with the input that you have sent in to the existing content of the RAG, right? And so we have exactly 10 of these as output because we set the top K as 10. So we only wanted to find the top 10 matches, and that's what we see here, the top 10 matches for our query in the RAG database. All right, so let's also take a look at how the output looks like from the LLM-based RAG retrieval. So this is that output. I've highlighted this in blue. And immediately, as you can see, this is much more nicer and cleaner than what we had before. And what's happening here is that the LLM model or the Gemini model has taken the output from the above details from the RAG, right? These chunks of information, and it has used the masked corpus of information that LLM model is already trained on to be able to generate this, pretty little information that would be very meaningful to humans. Right, and that's really the beauty of it is that not only the LLM is using its own knowledge, but it's also leveraging the RAG tool that has been embedded into it to ground this information on specific contextual information that the user wants, right? But this is still a very half-baked solution at this point because first of all, we're only doing it for the 10 nearest searches. We need to do more than that. And also, this is not taking into account the organizational best practices, right? Which is what we're going to see next in the next part of the video, where I'm going to ask this LLM to generate this information by merging with the company's organization policies or the company's security best practices. So let's do that next. Let me quickly summarize what we have done so far. So we started with 287 web documents around configurations for Google Cloud Storage buckets. We stored all of these documents in a bucket in a GCP project. From there, we created a RAG or vector database. We had two important parameters to keep in mind here, the chunk size, which we set at 500 tokens, and the check overlap, which we set at 100 tokens. From there, we saw that there are two ways to retrieve information from the RAG. One is using the LLM-based retrieval, where we use the Gemini AI LLM model, and another is the direct retrieval. In both of these methods, we said that the two important parameters is the top k is equal to 10 and the vector distance threshold of 0.5, which is kind of like a similarity score. And these two parameters help you to process or to filter this information from the RAG. And for the LLM-based retrieval, we use the Gemini AI model, and this resulted in a generic set of cloud security requirements for cloud storage buckets. And from there, now we'll take a look at how we'll convert these generic requirements into custom cloud security requirements grounded in a sample company's security standards. All right, so this is a sample of a cloud security policy or standards that you might see in your own company. And I've created the sample for Acme Incorporation, and as you can see, this is a standard for documenting baseline security requirements for the use of public infrastructure, right? So you might have similar policy standard in your organization, and what we want to do is we want to ground the generic cloud security standards using these custom policies that might be that will be applicable to your company, right? So this has different sections on different security domains. This is a section on IAM, similarly for data storage, logging and monitoring, vulnerability management, network security, and incident response, right? And this is not just one policy for everything in the company. This is obviously a pointer to different kinds of other policies. Like for access review, you need to read this one. For secrets management, you need to read this one, right? And similarly for data classification and cryptographic standards, right? So this is a pointer to other standards, but this is one document that stores all the cloud security standards that you should be mindful of when you're using public cloud for Acme Incorporation. And what we want the LLM to do after it, assesses this policy against the generic cloud security requirements is to ground those generic cloud security requirements with the information here. So, for example, when we have a requirement that says, hey, the GCS bucket should be encrypted with cloud KMS key, then the key should meet this particular policy for storing and rotating encryption keys. Um, and similarly, if we are saying the GCS bucket data should be backed up, then it should be backed up based on this particular policy, which is provided for Acme Incorporation. So what I have done is I have to convert this policy into a text format for the LLM. So this is how the policy looks like in the textual format. And next, take a look how we will be giving this as a prompt to the LLM to be able to ground our generic cloud security requirements with these company specific standards. Okay, so this is the updated script that we have for creating the custom cloud security requirements. And the first thing to note here is that we are using the direct RAG retrieval method here. We are not using the LLM based retrieval. And the reason for that is because I want the output of this direct retrieval to be part of my prompt window directly. And if you have worked with LLMs before, you would know that the longer the prompt, the more information the prompt has, the easier it becomes for LLM to answer your question, and the accuracy of the answer increases significantly as you increase the prompt window. So by providing these generic cloud security requirements as part of my prompt, I am increasing the accuracy of the answer that LLM generates. So that's why I'm using the direct context retrieval method here. And the other difference here from previously is that we have the top K as 30 here. So I want to retrieve the 30 most closely related finds from the RAG to this particular text, and the text is exactly same as before. We're also opening the cloud security standards text file and copying it locally and passing this variable to our prompt as well. So the major work that I have done is updating this prompt uh, to in a way that it could be uh, very useful for the LLM to be able to generate the cloud security requirements, right? So what I've said is that, hey, our goal is to generate a list of security requirements for Google Cloud Storage Bucket. Below is the security requirements for storage bucket retrieved from GCP best practices. This is our direct retrieval from the RAG. Below is the full company standards document. Enhance the Google Cloud Storage Bucket security requirements based on company specific standards that are applicable to storage type of services. There is more than one type of cloud service guidance available in the standards documents. It might be for compute and databases. So it helps to mention the type of service here. If the company standards add extra security controls or modify the requirements, update them accordingly. Provide a final version of the security requirements that align with both GCP best practices and company policies. Create a tabular format that could be easily exported as MD file. So as you can see, a lot of work was done on the prompt, and this is also a very important part of LLM based tooling, the prompt engineering. So be careful with this prompt window and how you define it here, because that will directly correlate with the accuracy of the final output. So having done that, let's see how the output from this now looks like. Okay, so now I'm going to run the script and I'm going to store the output in an MD file. And this is just so I can open this in a GitHub window and show you how cool and pretty the output looks like. Yeah, so the script was done running and opened the output in an MD file here. And let's read how it looks like, right? Okay, here's a table of security requirements for Google Cloud Storage buckets enhanced by the Acme's public cloud standards. I have focused on requirements that are directly applicable to cloud storage buckets and combined best practices with the Acme standard, right? So this is exactly what we wanted. Now we have the security requirement here. We also have the justification. The source of this could be from GCP best practice, or it could be from the Acme standard itself. So for example, Acme standard 2.1, if I open this in the standard itself, this is the one. It talks about data classification and how it should be done based on SEC 101 data classification policy. And that's exactly what our requirement right here says. Um, Classify all data stored in the bucket according to Acme's data classification policy. Um, so this is pretty interesting, right? So these are all like GCP best practices, as you can see, and there are some which is coming directly from the standard. There are some which is a mix of both. For example, encryption at rest is a common control that's available in GCP documentation, but there is an encryption risk specific control here which talks about for data that are classified as confidential by Acme, they should use Acme's KMS solution for client-side encryption. So this is pretty interesting. This is exactly the kind of control that developers or engineers in Acme company would want to see. If you give this document to them, they can try to enable this by default in their implementation of GCS. So this is actually something that could be used by a majority of teams, right? And let me go down and show you other stuff here. Key rotation, again, it points out that it should be based on Acme's cryptographic key management policy. Um, Similarly, also let's see logging, for example. So logging is a common control in GCP and other cloud environments, but then it goes and expands that to say that platform level storage logs must be stored using persistent cloud native storage and integrated with Acme's centralized logging solution. So this is another example of how the AI has merged these two requirements from these two different sources and created this custom cloud security requirements list, right? So one more caveat that I would like to point out here is that this is not the end all be all, right? This is not something that you can just hand over to developers and say, hey, implement this in production. This could be the starting point of that conversation. We need humans as part of this loop because some of these mappings, as I said, this one is inaccurate, for example, right? So you need human feedback, somebody who is a subject matter expert, has expertise in security to be able to review this and confirm if there is no hallucinations or things like that with the LLM model, right? So we definitely need human in the loop after this, but this is again a very good starting point to create these custom requirements very easily. You don't have to read 287 documents to do this. You can have the AI read those documents and be the starting point for your cloud security requirements creation program. All right, so let's do a quick summary of what we did in the video. We started off with the problem that companies migrating to public cloud have a challenge in creating these company specific custom cloud security requirements because of the huge number of services that these cloud providers offer and the huge number of documentation or different ways to be able to configure those services. So we wanted to explore how AI can make this job easier. So we started off taking the example of Google Cloud Storage bucket, and we downloaded 287 documents for configuring these buckets from the internet, and we created a RAG or Retrieval Augmented Generation database or vector DB from those documents, right? Then I showed you a couple of different ways how to extract this information from the RAG, and then we used a GenAI LLM model to retrieve the information from the RAG, and we coupled this information, merged this information with the corporate security policies, and created a beautiful prompt for this LLM model, and eventually we're able to create the company specific cloud security requirements from there. So that's it, guys, for the demo. Thanks for watching, and keep subscribing to my channel for learning more about cloud security and how AI is continuously evolving this field.